Cool, my name's Rishal. I'm doing the talk on neural networks. A bit of background of where this talk came from was I noticed a lot of my colleagues that are developers have had a little bit of a tough time getting their minds around neural networks and machine learning, and it usually is related to the math. There's a lot of math involved. So this talk is meant to kind of demystify the underlying math in neural networks and give you some intuition as to how they work and how you can use them in your projects. So a little bit about me. I'm from South Africa, so I've come all the way to Porto for the first time. It's pretty great to deliver this talk. I work at a company called Intellect. It's basically a custom software engineering company as a solutions architect. I've worked in a range of different industries: agriculture, finance, health, gaming, which has given me a lot of perspectives on data and on businesses. I also have a little startup where we try to build products that we have ideas for. I'm also writing a book with Manning, so keep an eye out for that. It's called Grokking AI Algorithms, which should be in early release soon. Also run a community in South Africa called Artificial Intelligence South Africa, where we host monthly meetups and hackathons and workshops to help developers understand more about AI and machine learning and how they can incorporate it into their day-to-day. And lastly, I like traveling, I like exploring, learning about new cultures. I spoke to some great people yesterday who told me quite a bit about Porto and Portugal. It was really fascinating. But yeah, enough about me. Let's talk about AI and neural networks. So first, before we talk about artificial intelligence, let's try to figure out what intelligence is. So here's a quote by the late Stephen Hawking. Intelligence is the ability to adapt to change. So he focuses on adapting to your environment as being intelligent. Salvador Dali, he focuses on ambition. He says to be intelligent, you need to have ambition. Einstein says imagination. So you can see there's these conflicting views of what intelligence is, but what we know is we base our understanding of intelligence on ourselves as humans. We believe we're the most intelligent life form, and we are the benchmark for intelligence. So it's very difficult to quantify this, and if you speak to a lot of professors or people in academia, you'll find that everyone has a different view of what intelligence might be. So let's have a look. When we talk about AI, let's just understand that intelligence is something that is a little bit fuzzy for us to define. But let's do some examples here. If we look at AI and we've got a spreadsheet of data and we're generating a report from that spreadsheet with some intelligent queries, would you think that's AI? Yes? No? Probably not, right? It's just kind of transforming data. What about routing? When you pull out Google Maps and you're going to be getting a route through a city or through some roads, would you think that that's AI? So there might be some algorithms in the background helping with this. Maybe it is, maybe it's not AI. How about a chatbot? When you're interacting with a chatbot on your phone or on your browser, could that be AI? It could or it couldn't, right? A lot of chatbots just use decision trees. It's a bunch of if statements. So it's this illusion of intelligence. What about blockchain? Is blockchain AI? See, all the buzzwords. But how about this? When you're working on your phone and you're using Snapchat and there's a filter and it modifies your appearance, would you think that's AI? Possibly, right? A lot of the modern AI work with imagery. Maybe it is AI, maybe it's not AI. How about a bot that chooses to buy or sell stock based on past performance, based on things that are happening around the world? Maybe. How about a game, an AI that plays a game like StarCraft or Dota? You've probably seen that from OpenAI and Google DeepMind, right? Maybe that's AI. How about something that looks at brain scans and finds tumors way better than doctors can? Right? Optimizing cellular networks or self-driving cars. Or even if you've watched Netflix, the way they make recommendations to you. Or right now, what they're doing is they have interactive shows which give you options based on previous selections that you've made in the show. I have a theory that they're collecting that data to psychologically profile us, to give us better shows or more interesting interactions. So you can see that this line between whether something is artificial intelligence or not is very blurry in tech. But it's not just in tech. There's intelligence all around us. Ants, a single ant, if you held it in your hand, you wouldn't think it's very intelligent. However, in groups, they can do really amazing things, build really interesting and effective colonies. And they do this with something very simple. They have 10 to 20 different perfumes that they drop around as they walk. And through those 10 or 20 different perfumes, they can communicate these different actions, or they can alert an ant that something is wrong, avoid this area, or recruit ants to help them collect food, or show recognition to ants for doing a good job. And you can tell that this is something we do on a daily basis with our colleagues, with our families, but we do it verbally, or we do it with gestures. Whereas ants do that purely through pheromones, which is quite amazing. Okay, how about the human brain? If we had to compare our human brain and our human forms to a computer, our processing power in each and every one of you is 1 exaflop. Do you guys know what an exaflop is? It's a billion operations per second. There's not a single supercomputer in the world that is as powerful as a single human brain. Right? If we had to figure out what kind of RAM we have, it's about 2.5 petabytes of RAM in your brain right now. That's about 210,000 DVDs. And these are your these deep connections between your neurons in your brain that give us this amazing RAM that we have. And hard drive. If we look at our DNA and think that our DNA is hard storage, we store 150 zettabytes, 256 billion DVDs. So there's scientists actually trying to store digital data in organic DNA in storage for hard storage. Right? So you can see as a single person, you're a really powerful computer. And a lot of the time, people think there's this danger of AI, and they might be able to do things that are, might be scary or might be harmful to us, and that is true. But if you look at it this way, as us just being these amazing organic computers, there's still a way off before a computer has these kind of specs, right? So when we talk about intelligence, in some of the examples I just gave, so if you're working with brain scans or if you're working with cellular network towers, that's an example of narrow intelligence. If you built an algorithm to work in that context, it can't generalize. You can't take a cell network optimization algorithm and go detect brain tumors with it, right? So this is an example of narrow intelligence where you focus in a specific domain, a specific context, and build some intelligence around that. General intelligence is what we seeing as AI, or the future of AI, where we can take algorithms and generalize. And that's why images and some of the examples I showed you with regards to understanding human faces, understanding a game of StarCraft, why it becomes so interesting, because this is how we do it. When you're a child and you touch something hot, you know not to do it again, but not specifically with that object, but with anything in that feeling that's a little bit hot, right? You've learned to generalize. And that's what we're trying to achieve, especially with the StarCraft bot. The bot literally just watches a screen and learns from that. It does not integrate with an API or anything of the sort. It literally learns from looking. Okay, and then we have superintelligence, which we don't know what it could be. As I said, general intelligence is our benchmark. If we even get to superintelligence, we might not even know it. Right? We might not even be able to understand it. So let's not worry about it for today. One interesting fact is you can measure general intelligence. There's something called a G factor, general factor. It's used with rats, with apes, as well as humans. And it tests your spatial reasoning, your cognitive abilities. So there is a way to measure this. So when we do develop algorithms that behave this way, we can measure it and determine how good is this algorithm at being general? How good is it at being human? So to sum up some of this theory, if we talk about AI, inside of AI we've got this discipline called machine learning. And inside of machine learning we've got deep learning. So these examples that I talk about with imagery, a lot of that is deep learning, which is a sub-discipline within machine learning. And neural networks is used throughout artificial intelligence in different ways and different forms. So let's have a look at machine learning to start with. If we have this chart and we went to the store and we've gathered some apples and oranges, we've weighed each apple and orange, and we've also determined, is it a smooth texture or is it a bumpy texture? And we want to figure out, can we generalize and know that something of a specific smoothness and a specific weight is likely going to be a certain fruit? So perhaps something that's a little bit heavier, that's a little bit rough, is an orange. And if you plot this on a chart, on a graph, what machine learning at its simplest form is trying to achieve is finding this line between these two categories of data. And whenever there's a new data point, if it is there, it knows it's not an orange, it's an apple, right? And you'll see that there's a lot of errors here. There's some orange that is on the other side of the line. And this is something so common to machine learning, because if you don't have that, you run into a problem of overfitting, where you've learned so strictly on a set of data that if we introduce an orange, that's a little bit of an anomaly. It doesn't classify it as an orange. But we'll get to that in a bit. So that line was pretty easy to compute. We could sit down with some paper, draw that line, and figure out what that function would be. But what happens when the line looks something like that? It becomes a little bit more difficult to compute that, but still doable. What happens when it's like this? It starts getting a little bit more complex for us to compute this by hand. What happens if we have a 3D space? Maybe we've got smoothness, we've got weight, and we've got dimensions. You're going to have to draw this plane over this graph to classify where do our apples fit in, where do our oranges fit in. And this becomes very difficult for us to do. And this is the entire point of machine learning algorithms or training models, to look at the data and figure out this plane or these lines so that we can categorize the items in there. So let's look at some steps in machine learning. And if any of you have experience in it, you'd understand that the cool stuff is generally what you do the least of. A lot of it is collecting and understanding your data. So if we want to do data on pollution in the ocean, we need to actually be a little bit of domain experts about the sea and what are the chemicals, what are the life forms in the ocean, how do these things interact. You'd probably have to consult with a marine biologist to help give you some insight into that. Without having this understanding of the data, you can't build a model that's going to be accurate. So preparing your data, if you've not even worked with machine learning but worked with any sort of system that had data, you'd know that data is not perfect. You've got nulls everywhere, you've got empty strings, you've got something that says Porto in lowercase, Porto in uppercase. One of it starts with an uppercase P. Data is not generally clean. And for us to make it useful, we have to prepare that data in a way that a computer can understand that Porto represented in these different forms still means the same thing. Then we get to the interesting part of training a model. Like I described just now, we've got our apple and orange data. Now we want to train this model. And all that model is doing is figuring out those lines and those planes for us, specifically with supervised learning. Next, you're going to evaluate the model. So you're going to give it data it hasn't seen before, it hasn't worked on during training, and determine how is it classifying these items. If you bring in a whole new batch of apples and oranges, is it performing well? Is it classifying an orange as an orange? And then almost all the time you're going to improve the performance of that model. And that might involve going all the way back to collecting more data. It might be preparing your data differently. It might be using a different model. So this is the general life cycle and steps in any machine learning endeavor that you might take on. So let's look at how we would train a model. There's a bunch of different machine learning techniques, including linear regression, logistic regression with decision trees. There's a whole set of algorithms that are useful for different purposes. And the one that we're going to look at today is neural networks. So understand that it's just one of many different approaches you can take. It's not a silver bullet. If you want to do something quite simple, you need to understand these different algorithms, and perhaps the simplest one, like linear regression, might be the one for you. Okay, so a little bit of history about neural networks. It's not something new. The first model of a neuron was studied or published in a paper in 1943. Okay. In 1951, Minsky described the first artificial neural network. In 1958, a researcher by the name of Rosenblatt introduced this concept of a perceptron. It was modeling a single neuron of a human brain, generally, and he actually believed that he solved AI. He thought that anything could be learned through using that perceptron. A big problem was that it could not solve an XOR problem, right? Nonlinear problems, it ignored. It could not perform there. And unfortunately, Rosenblatt passed away in a boating accident before he could even defend or work continuously on this idea of a perceptron. And there was this idea of an AI winter. For quite some time, there was a researcher named James that did some work on how our brains think and how it works and tried to apply that generally. How could we mimic that? And also in the 80s, these two researchers, you might know Likun, who works at Facebook right now, they created this concept of backpropagation together with Rosenblatt's perceptron model, and it performed really well. They created these tips and tricks over a whole number of years, and you'd notice in around 2006, you saw that ghost-looking faces that identified kind of outlines of faces and eyes. That was some of their work that they've been doing since the 80s. So the idea of neural networks is nothing new at all. So why is it popular today? And my opinion on that is that abundance of data. We have data that we've collected with the rise of the internet, data from individuals, data about companies, data about how people behave on the internet, data about how people behave in real life. We've got this abundance of data and better computing power. So back then, we needed a big supercomputer or something to compute a neural network. Now I can do it on my laptop. I can even do it on this little drive. So this is a neural compute stick. It's literally a USB drive. I plug into my MacBook, and it performs 5 times better at computing neural networks, right? And lastly, business opportunity. If there wasn't any idea for earning money or doing something useful or making better decisions using artificial intelligence and machine learning, we wouldn't be doing it. So I think these 3 factors have made it a viable option for us to pursue in 2019, and now that it's become really popular. Okay, so let's look at how a neuron works. So this is the general structure of a neuron, and we have billions of these in our heads. There's this concept of dendrites that receive electrical impulses, electrical signals. There's a cell body that interprets these signals from the different dendrites, and then it decides how much of that signal do I pass on to the other neurons. It passes that on around something called an axon, and then touching the other neurons is something called a synapsis. And when I say touching, there's actually a little gap between them, and this synapsis adjusts the amount of the signal that's passed on again, right? So the way we think is actually billions of these little neurons just passing around these impulses. And depending on how strong certain neurons are, we have certain perceptions or certain memories or certain ideas of how to do things. So in the example of when you touch something hot, you will burn yourself, that is something that's been encoded in this nucleus to say, don't pass the signal as really strong because we shouldn't be doing it. And it's a whole bunch of neurons that work together to give us that feeling, give us that thought. So how would we model this in a computer? Well, this is exactly what a neuron would be represented by. If we look at these as the signals coming in, there's a certain weight that gets added to them. That's the weight of the synapses. It's affecting the input signals. We sum up those weights. So we decide we're getting all of these inputs. We need to sum our inputs multiplied by our weights. So you would multiply x0 by w0, x1 by w1, so on and sum those numbers. All right? And then you have an activation function. This basically decides, based on that summed value you received, what should I do? How much of a signal should I pass on to the output? So let's put some real numbers in here to give you a better idea of how that works. If we've got 0.15, 0.5, etc., and these are our weights, to calculate the sum, we would multiply 0.15 by 0.22, and we get 0.033 down there. We do that for each input and respective weight, and we get the sum of 0.683, right? So all this part of the neural network is doing is it's taking the input, multiplying it by a weight, and summing all of those values. Next, we have an activation function. So a common activation function, or a simple one, is a step function. So if we have a positive number, return 1. If we have a negative number, return 0. In this case, we have a positive number, which is 1. So we return 1. And our output is 1, right? So this is the simplest form of a neural network that you would find, and it's called a perceptron. This is what Rosenblatt invented all those years back. And an actual neural network that we use that's useful to us is really just a combination of many neurons. So if we look at some code here, this is some Python code. It's as simple as creating an input layer that's described as an array. We've got a layer that includes the weights. We're multiplying the inputs by the weights. We're then summing those values. And then lastly, we're doing the activation function, which is a useful function from NumPy called Heaviside. It will give us that 0 or 1. And in just 5 lines of code, we've written a little neural network, a little perceptron. This could actually solve our problem with the apples and oranges, right? So something as small as this could be useful to us. So again, if we want to get that line, this perceptron would be quite useful in doing that. Now, a little bit about activation functions. You've seen the step function that we just used. If positive numbers are 1, negative numbers are 0. There's others that are useful in different contexts, which I'll show you why in a bit. One is the sigmoid, which is a lot smoother line. We don't have to be strict and say 1 or 0. We can give a range between that based on the input. Or a hyperbolic tangent. This is similar to the sigmoid, but it goes down to -1. And they each have different uses based on the data that you're working with. So let's look at some data, and let's look at how we would use a trained neural network. So we're going to assume this neural network has been trained. We're not looking at the data. We're just using a model that someone else has created for us. First, we need some data to work with. So imagine we've got these 4 properties it could be someone driving. If we recorded people driving or self-driving cars, we're saying if a car was driving at 40 miles per hour on half-decent terrain with 180 degrees of vision and 50,000 miles of driving experience, when it encountered a situation where it might collide with something, did it collide or not? Okay, and in this case, we're going to say, we know from all the data we've collected, it's a 0. It didn't collide. Whereas this one, driving at 70 miles per hour on very poor road quality, with very poor field of vision, with more experience though, and in that same situation, it did collide. And now if we look at this as humans, it's easy to see why that happened. The person was driving really fast on really bad roads. Okay, so it's almost obvious that a collision would happen if they were in that situation. And I've done this for a reason, just so we can do some intuition about this. This one, 5 miles per hour, it's driving pretty slow. You don't really expect a collision to happen. Okay. So how does a neural network work with this data? We need to standardize and scale our data. So a computer doesn't know what miles are. And maybe people in this room also don't know what miles are. I also use kilometers. So a computer doesn't know what miles are. A computer doesn't know what degree of vision is, right? So the typical way to represent data is something between 0 and 1, or -1 and 1. And now you can see why the activation functions can differ. Based on how you've scaled your data and what data you're working with, you might want to use different activation functions. So how would we do this? What I've done is, for the first property, the least you could travel is 0 miles per hour. Okay, you can't go slower than that. And I've made the maximum 70 miles per hour because that is a legal limit around the world. You shouldn't drive more than 70 miles per hour. So let's assume that everyone obeys the rules. The next is terrain quality. That one's easy. We've got a rating from 0 to 10, so it's really easy to figure out what the scaling would be there. Degree of vision, we can't have more than 360 degrees of vision, so we know the limits for that property. And lastly, we've got total distance traveled, basically experience in driving. You could have no experience, and what I'm saying is, if we have more than 300,000 miles of experience, it doesn't matter. We're saying 300,000 plus is fine. We're going to treat everyone the same. You've got a lot of experience. And you can see why you need to understand your data, you need to understand your domain if you're going to do something like this. If I had no knowledge about cars and no knowledge about driving, I might say that, okay, we'll make the maximum miles per hour 10,000 just to be safe. But that doesn't make sense, and you're skewing your algorithm because you don't understand the context that you're working in. So it's really important to understand your data and understand the business or problem space. Okay, so if we have to scale this now, if we look at our first entry, we would scale it like this. We'd take the input, in this case, which would be 40 miles per hour, minus the minimum, and we'd divide that by the maximum of that property minus the minimum. So if we look at our current speed, min is 0, max is 70, we would do 40, which is the actual input, minus the minimum, and then we've got 70 minus the minimum. So we end up with a value of 0.57. Okay? And we would do that for all of our different properties that we have in our data set, and you can see that everything is now a value between 0 and 1. We're happy because a neural network can understand that. It understands everything is scaled. It doesn't need to understand what miles are. It doesn't need to understand what degrees of vision are, etc. And again, that's really simple to do in some code. Nothing too complex there. So once we've done this with all our data, we get something like this. Everything is something between 0 and 1. Everything is nice and standardized, and we can now start using this neural network. So much like the perceptron, when we're using a neural network, we need to define the inputs. Now, in the previous example, we randomly had 4 inputs. We didn't know what those inputs were. Now, this is going to make a little bit more sense because our inputs are the different properties that we're working with of the data, the different features of the data. So we would have only 4 input nodes, which is each property that we're working with, current speed, terrain quality, degree of vision, etc. And then we've got this idea of hidden nodes. To simplify this in your mind, each of these nodes are simply just a perceptron that we've seen already. We then have connections between every input node to every hidden node. Okay, every input to every perceptron. And then finally, we've got one output. So to keep it simple here, we just want to decide, will something collide or not? We'll talk about multiple outputs in a bit. Okay, so to recap, input nodes are your features. You've got weights between every input node and every hidden node. And then you've got your hidden nodes that have your sum function and your activation function. And then lastly, you've got your output that will hopefully give you a correct prediction. But let's dive into this. How is this working? Why is it intelligent? Okay, if we had to make some assumptions. Now, when we use a neural network, you'll notice that the weights are very different for each connection between an input and a hidden node. Now, perhaps there's strong connections between these two, terrain quality and degree of vision, for this hidden node. intuitively, what is it doing? It doesn't care about the other properties. What it cares about is, what is the relationship between terrain quality and degree of vision when accidents occur? Okay, maybe that specific node, all it cares about is those two properties and the likelihood of an accident occurring. Perhaps for this node, it's looking at terrain quality and total distance traveled. What is the relationship between those features and collisions? And similarly, maybe this one is current speed and terrain quality. It tries to figure out, do more accidents happen at higher speeds on poor roads, right? That might be the intuition of these different hidden nodes. And I say intuition because this is something that gets built up while training it. And from analyzing it after, you as a human might look into it and realize, okay, that's interesting. This is what these different hidden nodes are trying to achieve. And together, just like the ant, and that's why I like that ant example, a single ant might not be able to achieve much. You saw that with the perceptron. But multiple perceptrons, looking at different perspectives of your data, that's what makes something intelligent. And that's why neural networks perform well, and that's why we use them. So a little bit about the terminology used, or the maths. So inputs are typically denoted by x. So we've got x0 to x3. Hidden nodes are denoted by h. So we've got h0 to h4. And your output is usually called y. So if you're thinking a little bit about maths now, you can see how it's kind of resembling a function, right? A mathematical function. Okay, so as I said, once you've trained this neural network, your weights might actually look like this. I've darkened some out. You might have weights that are very insignificant to these hidden nodes. So again, H0 just cares about H1, H0 cares about X1 and X2, right? It might have very weak connections with the other input nodes. And your weights are typically denoted by W. So you'd have W0, W1, etc. Okay, and sometimes we've got this idea for weight bias, where we add or subtract a specific weight to do some arithmetic with all of the weights going to your hidden nodes because we want to sway the decision. And again, if you understand your data and you understand and you're tweaking it and you're figuring out why is it not performing how I want it to perform, you might want to add something like this. But we're not going to get into that detail going further, but just remember that there's this idea of a weight bias. Okay, so now if we've got our input nodes, we've got our weights, and we've got our hidden nodes. How is this going to work? So let's plug some numbers in there. In our first example, where we've got our speed at 0.57, remember we computed this at the standardization slide, and then we've got half-decent terrain quality, we've got 0.5 degrees of vision, and we've got that much driving experience. And let's assume that these were the weights that were trained by our neural network. Remember, we're using it, we're not training it. We're going to get that value when we do our sum function, 0.0165. This means that we've multiplied the input from 0.5 with 0.01, and we've added it to 0.5 multiplied by 0.023, and we get this sum. Just like we did with the perceptron, simple stuff. And we would do that for all of the different nodes, okay, and we get that value. But we now need to add our activation function. So in our case, we're not going to use 0 or 1, the heavy side or threshold one. We're going to use the sigmoid function that we saw, which gives you a nice, smooth value. So might give us something, might give us 0.5, might give us 0.2, but it's going to be a value between 0 and 1. So in this case, we get 0.5041, okay, for that specific hidden node. Again, this is exactly what we were doing with our perceptron. And we would do that for every hidden node, and we get all of these values. To determine our output now, since we have more than one hidden node, we have to sum all of that. Okay, we've got 2.5 or so. What does that tell us? Doesn't tell us anything yet, because we have to apply the same activation function to that hidden node now, since we've summed everything. Now we get this value, 0.9253. What does that tell us? So that's telling us there's a 92% chance that an accident would occur, that a collision would occur, right? So based on these weights that have been trained for us and the specific input, it's giving us a prediction there. And it's a 92% chance that an accident would occur. All right, does that make sense? Okay, so now we see that using a neural network, all we're actually doing is we're using those weights that were trained by something, okay? And we're going to get to the training in a bit. But when you're using something, you don't actually care about the weights, you just care about what it's trying to predict for you and what data it expects. So let's get to the scary part, that every time you look at neural networks on the internet, you say no because there's too much math. Let's figure that out. So firstly, we just need to understand a little bit about data types. We've got scalars, which are just numbers. Everyone's used to that. Vectors, you're all used to arrays in whatever language you might be coding in. And then we've got two-dimensional arrays, which are called matrices. And another word for them, if you didn't know, is called second-order tensor. Okay, so your 2D arrays are actually second-order tensors. And then we get to something called a tensor, which is, you might have heard of TensorFlow. It's really just a multi-dimensional array of vectors, scalars, and tensors of varying dimensions. What's interesting is, as humans, we can easily see a number and imagine a number, or imagine an array, or a two-dimensional array, or even a three-dimensional array. We can plot that. But when it gets to something like this, it's in dimensions we can't even wrap our heads around. And you might have heard of TensorFlow. This is something that's really good at computing these matrices and these different types of dimensional arrays. So with that in mind, let's see how we would understand the maths behind this. If we've got our input nodes, that's really just an array. We've seen that. Our input nodes are an array of values. And then we've got our weights. And we've got a weight between every input node and every hidden node. So we've got something that looks like that. For x0, we've got weight 0, 1, 2, etc. for every hidden node we have. So we now have a 2D array for our weights. Remember our weight bias. We might have this weight bias involved, so we would add that. Okay, so we're going to multiply our x by our weights, and we might add a bias. What else do we do in the hidden node? We do our sigmoid function, or we do an activation function. Okay, so we do that activation function on this whole equation, and we get an output. So if we had to simplify this in maths, mathematically simplify it, but when you look at it, it doesn't look so simple. But with this intuition, you can see that this is really just representing this, which is that visual network that we've been working with. And if we summarize that, we get that. That mathematical expression describes our neural network. So by understanding it visually, how these nodes interact with each other and how this works, when you look at the math now, you can see it's actually quite simple, what this neural network is doing. Okay, so now we get to an interesting part about training a neural network. So we've understood how we're going to use a trained neural network. How do we train it? Okay, and this is the interesting part. This is the work that was done in the 80s regarding backpropagation. So this whole training step is centered around backpropagation. So again, let's imagine we have our little perceptron. It's just a single node in there. Something's changed now. We now have something called y hat. And y hat is the difference between what you expect the value to be and what the actual value is. Sorry, that would give you the cost. So your cost is calculated by when we run values through here with some randomly initialized weights. What value do we get, but what value do we want? And we determine a cost, right? So for example, and that gets propagated back to the weights. So for example, if we had these numbers in there, and these were randomly initialized weights, and a rule of thumb is you want to randomly initialize your weights to something close to 0, but not 0. Why would that be the case? Because if you've activated it with 0, you can't really change it. Anything multiplied by 0 is 0, right? So let's feed this through our randomly initialized neural network. We get this value of 0.664. But we know from our training data that given these numbers, given these values, an accident definitely did occur. So what needs to happen? We need to calculate the cost. We're essentially calculating how wrong are you? How wrong is this network? Okay? And the only thing we have control of, or the only thing the algorithm has control of in this network is the weight. So we calculate the cost, and we propagate that cost back to these weights. Okay? So we said, this is how wrong you are. Please update yourself to be more accurate. And these weights will then adjust themselves, and the next time you run this through, it will be more accurate. It might give you a number that's much closer to 1. Okay? So when we're working with our larger neural network, the principle is exactly the same. You figure out what the cost is, and you push that back to the hidden nodes weights. The only difference now is we've got lots of different weights that need to be updated, right? So based on some cost, a whole bunch of weights need to decide, how am I going to adjust myself to accommodate for this? And remember, they can't all wildly update very dramatically, because that's going to throw the whole thing off. They're going to make small adjustments through training to refine what their weights should be. So we go through each example, and this is now our training data. We're telling the neural network, here's the inputs of current speed, terrain quality, degree of vision, distance traveled, and a collision did occur, or a collision didn't occur. And through many cycles of this, those weights start getting refined, and the neural network understands these relationships between different features in your data. Okay? So again, you push it back, the weights update. Now an interesting thing is, how are the weights being updated? Are you just adding stuff or subtracting stuff? How are you doing that? If we had to plot, or if we had a bigger network and we had to calculate the weights for all of this, all of these hidden nodes, right? You've got, 56 weights that you need to compute. Do you think we could brute force this and just try every value between 0 and 1 for every weight and every combination of that? It would literally take you probably thousands of years to compute this on the best supercomputer we have. It sounds simple, but imagine comparing 0.11, 0.21, 56 times every combination. It's ludicrous. You'd never be able to do it, right? So how do we get past this? How do we solve this with neural networks? Well, we want to plot the error, and this is where a little bit of more maths comes in. We want to plot the error. So given a certain input, if we have our error, given a certain weight, our error is over there, or maybe our error might be over there. Okay, you're just plotting it on this graph. Or it might be over there for that same weight, right? It might be changing all the time. Each weight would be represented by a function, and our function might look like this, right? This one's a pretty simple one. So if our weight is in this top corner of this function, what we want to try and do is get the lowest error rate. Okay? So whether we like it or not, all of the weights in our neural network would be represented by some sort of other function. It might look like this, it might look differently. This is going to be in the universe represented on this plane. And we want to get our weight down here, but we don't know what this function is. If we did, it would be easy. So what we do is we use something called gradient descent. You might remember this from calculus. All we're doing is we're calculating the slope at that specific point. And if it's a negative slope, we know we need to move right, because our minimum is to the right of us. If it's over there and we get a positive slope, we know we need to move left. It might ring some bells with if you've done some calculus before. And you keep doing this, and what ends up happening is with just a few moves of moving towards the bottom using this gradient descent method, you will find your optimal weight with the lowest error. One thing you'll notice is your error is never going to be 0. You're always going to have some sort of error rate. If your error rate is 0, again, you're overfitting. You've learned too much on that piece of training data that when you get into the real world data, you might make very bad predictions. So this is a simple one, right? What happens if our function looks like that, which is more realistic? Okay, it might be something very weird like that. And we start off over there, and we use gradient descent. What's going to happen? It's going to fall into this trap, because it's a local minima, right? It's going to move down, it's going to think, I'm at the lowest point I can go. And that's where a technique called stochastic gradient descent, which is still using gradient descent, but using a little bit of randomness to get you out of these holes, right? Out of these little local minimas. This is where you want to be at the global minima. So stochastic gradient descent helps you do that. It works very similarly to standard gradient descent. So you can see now how the weights have these different values, and they know what their error rates are, and now they're moving on this plane to try and figure out where they should be. Okay, so now when we update it, what we do is we simply find the negative slope with that cost that we had, right? We've calculated the cost. We find the negative slope, and we simply add that to our weights. And you can see they get adjusted as we go along. Okay, and we'll do that for all of the weights based on all of the negative slopes for the cost function every time you go through an example. So every time we're going through one of those examples, we're computing this, we're calculating the cost, we're pushing that back to the weights, and we're updating it using that little method that we saw now. Okay. So what we've just seen is an example of supervised learning. This is where you use training data to train those weights on a neural network. And this is something that's generally most useful in our projects and in the work we do. There's a concept called unsupervised learning, where you don't have labels on your data. So in our use case here, we would not know if a collision occurred or not. What unsupervised learning is useful for is revealing trends and patterns in data that may not be apparent to us as humans. There might be trends that you find that you would actually never find unless you use an unsupervised learning algorithm to find those patterns with you. Another important thing is with supervised learning, you have a question to ask. So here we had a question: will this car collide or will it not? In unsupervised learning, you're actually trying to find the questions that you might want to ask. Right? You don't know what the questions are. And then another popular one is reinforcement learning. This is based on behavioral psychology. It's a rewards or penalty system. So if the algorithm performs well, you reward it. And if it doesn't perform well, you penalize it. And you might see this a lot with robotics, with games. You kind of let this agent explore a world, and based on how they interact with that world, you reward them or you penalize them. Much like a child. If a child does something wrong, or does something right, you might give them a sweet. If they do something wrong, you might give them a little smack or a strong talking to. That's that whole system of reinforcement learning. You're building strong connections between certain behaviors by that reward system. Okay, so when we're designing a neural network, to recap, this is a little bit more complex one to show you that these things have different architectures. One thing we must decide on is our data. We need to gather, understand our data, and understand our features that we're using. The next step is we need to normalize that input data, okay, so that we can work with it. We need to decide on the number of output nodes. Now, in our example, it was pretty simple. We knew that we wanted to figure out if this thing would collide or not. But what if you want to figure out, will this thing collide? And if it does collide, how severe or how fatal would the accident be, right? Then you might want to have two output nodes indicating would a collision occur as well as how severe the collision would be, right? It's important to note that this decision is based on the data you have. If you don't have the data to support that output, then it's not going to work. And this is why I say that fear of AI, like there's a lot of thought that needs to be put into here as a person. It's difficult. So building these networks is something that takes time and a lot of thought that needs to be put into it. The number of hidden layers. So perhaps you've got different relationships in your data, and you've got different layers that would be responsible for different things. And based on the number of inputs you have and the complexity, you might have one or many different hidden layers. Okay, then the number of neurons in each hidden layer. This is also something you can configure and decide what works best for you and your context. Also, the weight initialization scheme. So I mentioned the rule of thumb is to initialize it to something close to 0 but not 0. Right? But there's loads of different schemes that you can use based on your context. The activation function. So perhaps you want to use a sigmoid function there and a hyperbolic tangent there. It depends again on your data and what you're trying to solve. Your cost function. So you saw the cost function I used. There was a constant there of 0.5 that was added. And since it's added for all the nodes, it doesn't add any bias. It adds a bias to the entire network. So these are the kind of quirks you might also want to tinker with or tweak when you're optimizing this neural network. There's also something called a learning rate. So how quickly do you want the network to learn? Because you might have it update its weights too drastically that it doesn't learn correctly. So learning rate is also something that you can tweak. And then there's also stopping condition. Something can't train forever. Do we stop when it's finished with 10,000 rows of data? Do we stop? When do we stop, right? Do we stop when we've reached a certain accuracy? We say we're happy with 85%. When you've reached 85% accuracy, just stop learning. So there's various ways to control the stopping condition. If you want to get started, I would recommend Python as your base programming language. Python is quite developer-friendly, and a lot of the SDKs that are used for machine learning and neural networks are supported. NumPy, this is a great library used to work with multi-dimensional arrays and matrices. So you saw with our perceptron, we just use NumPy to help us with our arrays and the multiplication. So NumPy is a really good library for this matricey mathematics. SciPy, this is if you want to do some interpolation, if you're working with really scientific data and you want to make use of some built-in functions, SciPy is a good SDK for that. Pandas. So as I said, working with data is critical to this. Pandas can help you manipulate your data, normalize your data with very little code, as it has a lot of built-in functions in there for you. Being human, we want to see things, right? And so this isn't necessarily something required for neural networks, but if you want to visualize your data and understand your data, matplotlib is a really simple, easy library to get started. Scikit-learn. So if you don't care for the neural network stuff that I showed you now, if you want to try something really simple like decision trees, really basic machine learning algorithms, Scikit-learn is absolutely amazing. You can do something in 3 lines of code that's actually pretty powerful if you've got a simple use case. So I'd highly recommend that if you're getting started. And then TensorFlow. We spoke a bit about TensorFlow. It's a great library for computing these matrices. One problem is it can be overwhelming. You have to understand quite a bit of the mathematics to be able to use it or just read some of the code. And that's why I recommend Keras. It's actually written by someone from Google DeepMind. He also has a book called Deep Learning with Python. And he's written this abstraction SDK that sits on top of TensorFlow or any other computation engine. And much like how we were visually making our networks, you would code it like that. You would say, I want 4 input nodes. I want 5 hidden nodes. And in a few lines of code, you've built a TensorFlow network that would have actually taken you quite some time to write. And if you like Docker, there's a Docker image with all of these, or most of these SDKs already set up for you. It's called Deeper. So a quick one, just in interest of time, of how this stuff fits together. Base kind of a language and SDK. You've got some helper SDKs just to help us visualize and understand and manipulate our data. And then you can use scikit-learn if you're doing some simple work, or you can use TensorFlow and Keras if you're doing more in-depth neural networks. Okay, so quick one on some types of networks. We've got a recurrent neural network architecture. I'm not going to get into the details, but it's useful for figuring out memory. It almost has its own memory, right? So you've got multiple of these copies of this network that get adjusted every time you use it. And what this is very useful for is handwriting recognition, or audio recognition, speech recognition. So if you ever hear the word recurrent neural network, you now have something to associate it with. Another interesting one is a convolutional neural network. This is something specifically for images. So when you see image recognition neural networks, they all follow this architecture of a convolutional neural network, which tries to find specific patterns in images and relationships between those patterns. Okay, so quickly, let's look at some code. So I'm actually going to run it on this compute stick here. Okay. So what I have here is, this is the Intel Movidius compute stick, and they've got an SDK that you can use with Python. I'm not going to go through all the code. Basically what it's doing is you can open the device to make sure that you can use it. You can load a graph on that device. So what is a graph? It's our neural network, right? It's a neural network that we want to use. And since I'm super lazy, I'm just going to use Google's image recognition network. So you simply download it, and you tell the SDK to use that. Sometimes you might need to pre-process an image. You've got RGB images. Historically, I think it was Adobe who set a standard for BGR, and some of the SDKs just stuck with that. So you might need to do some image conversions or translations. And then you can actually determine what's in your image using that graph. Okay, so here we're using a library called Caffe, which is similar to TensorFlow, and we're using a graph that Google has already made for us. It's called AlexNet. It's something that won many awards for image recognition. So why would you spend all the time and energy trying to make your own algorithm? You probably don't even have the data unless you crawl Google for it. So Google has all that data. They've made this network, and they've made it available. So let's see it work. Okay, so all I'm doing here is calling the image classifier, and I'm providing a specific file. So just note I've named the files weird names, just so you don't think it's figuring out stuff based on the names of the files. So if we try to classify this owl, it's quite smart, right? Because it kind of looks like an owl, but it's told us it's actually probably a Persian cat or a kite, right? 50% chance Persian cat, 5% chance it's a kite, right? Let's look at another one. I've got a gang member, I think. Gang member, yeah. So in this case, it's only 29% sure it's an Egyptian cat. And I looked into this. It's actually recognizing the dog as an Egyptian cat and not the cat holding a knife, which is quite interesting. So one thing we can do here as well is we can get more than 2 predictions. So if we want to do 5 predictions, and let's do something a bit more futuristic. We've got the spaceship here, and it was 99.9% sure that it is an airship. 0% sure it's a projectile or missile. It's actually probably a very small number, not 0, but close to 0. But you can see that it's very accurate in some instances and not so accurate in others. The most interesting part about this, for me, is this 95 milliseconds to compute this. And that's running on this little flash drive looking thing. When I run it on my Mac, this is running in a VM. It takes far longer. It takes about a second or 2 for this thing to compute. So what's really cool is what's happening is different companies are making specialized hardware for you to run this stuff on the edge. We can have a drone that can compute neural networks. We have it in our phones. If you own the new iPhone 10, that has a neural compute processor on it. So that stuff can be really interesting going forward of what people come up with. I wanted to show you one that was quite interesting to me. So since we were in Porto, this was interesting. So for this one, it found that there's a seashore, a coast, a sea coast, and it was only 56% sure about that, right? But there's a picture I really liked. I think it's this one. Look at that. It's 26% sure it's a dock or docking facility. 22% sure it's a palace. In this case, it's very inaccurate about what it's seeing, right? And I think it's because this landscape is just so unique. There's nothing like it elsewhere in the world, which is very interesting. And I think the point I'm trying to make here is, regardless of what you think neural networks can do and what AI can do, there's still a lot of room for improvement. I think there's a lot of room for you to do interesting work and to explore and see how you can add your twist to it. So I'd urge you to try it out, explore it further. Here's some resources that I really like. An AI overview. There's a course called Elements of AI. It's free. There's also, for developers, Fast AI. It's also completely free. If you're interested in the academic and scientific side, I'd say brush up on your maths, linear algebra. Khan Academy is pretty great for that. I did a typo with the last link there, but there's a course by Andrew Ng. Very academic course, but if you go through that, you would be a wizard at neural networks. You'd be able to debug the math. But that's if you're interested in that. I think as a developer, you can get away with learning some of the theory, some of the math, and learning from implementing it in your work. Yeah, so I'd say find areas in your project where you can implement this, where you have data, where you can find these patterns, and try and make a responsible difference. Thanks for listening to my talk. I'd really appreciate it if you rate it. I'm always trying to improve. But thanks a lot.